The promise of deep learning, incredible accuracy, yet its reasoning often remains a frustrating enigma, a black box. This opacity isn't just an academic curiosity, it's a critical barrier in fields like medicine or autonomous driving, where trust and accountability are paramount. We need to know why a model made its decision. To bridge this gap, especially for image-centric convolutional neural networks, we turn to a specific class of explainability techniques designed to reveal where the model's gaze truly falls. Enter gradient-weighted class activation mapping, or Grad-CAM. It doesn't peer inside the model's neural pathways directly. Rather, it leverages the gradients of a target concept, flowing back into the final convolutional layer to produce a coarse localization map. This map highlights the important regions in the input image that most strongly contributed to a specific prediction. Think of it as painting a heat map, showing the exact pixels that truly influenced the model's classification. Python-centric frameworks like PyTorch Grad-CAM or TF-Keras make implementing this surprisingly straightforward. With just a few lines of code, we transform abstract predictions into visually intuitive heat maps. This seamless integration into the standard Python AI ecosystem makes Grad-CAM an accessible and indispensable tool for developers and researchers alike. Imagine a radiologist reviewing an eye-assisted diagnosis for a lung lesion. Grad-CAM doesn't just say malignant, it overlays a heat map on the X-ray, pinpointing the exact areas of concern. This builds confidence, aids in human-AI collaboration, and can even uncover subtle patterns in autonomous vehicles. It helps engineers debug scenarios where a model misidentifies an object by showing what the model was actually looking at. Unlike simpler feature importance metrics common with tabular data or tree-based models, Grad-CAM provides spatial and semantic explanations specific to visual data. It's not a numerical weight. It's a visual where, showing the exact locations that captured the model's attention. This granular pixel-level insight is a critical distinction, offering a depth of interpretability that traditional methods cannot provide for complex vision tasks. However, faithfulness in Grad-CAM explanations, its true reflection of the model's internal logic, is a subtle challenge. Explanations can sometimes be perturbed or misleading if the underlying model lacks robustness. This has spurred research into more rigorous evaluation metrics for explainability and the exploration of alternative approaches like counterfactual explanations, which identify minimal input changes that flip a prediction. Offering a complementary lens into model behavior, it's a dynamic area, constantly evolving. Explainability isn't a mere debugging tool, it's a cornerstone for responsible AI development. By demystifying the black box with tools like Grad-CAM, we build more trustworthy systems, foster greater human understanding, and unlock new avenues for scientific discovery, transforming AI from an inscrutable oracle into a transparent, collaborative, intelligent partner. True AI progress hinges on understanding